Okay, Ivan, whenever you want.
Okay. So today we have the pleasure to listen to Ilya Chevyrev from University of Edinburgh, and he will talk about reality structure for vector-valued SPDs.
Thank you very much for the introduction and for the kind invitation to speak at this interesting seminar series. So I'm going to talk about, this is, I forgot to mention this on this introductory slide, but this is joint work with AJ Chandra and Martin Heirer, who are at Imperial College, and with Shen at Wisconsin Medicine. And I'll be talking about a recent, part of a recent work that we did, which is an attempt to extend the formalism for renormalization and regularity structures to the case where these stochastic PDEs that we're often interested in take values in vector spaces, as well as the noises driving them. Okay, so I also don't have a contents page, so I'll just briefly say what I'm going to, the structure of the talk now. So I'll first concentrate on just the motivation behind what it is that we want to do, and give some ideas of the elements that appear there. Then I'm going to discuss a few details of the construction, but I'm not going to go into all the details that enter there, but just to give you a flavor of the kind of things that appear. And then in the last part, if there's time, I'll apply this formalism to a very specific example, which is the example that motivated us to look at this construction, which are the stochastic Yang-Mills equations. Okay, so let me start. So in the first part of the talk, I'll just be interested in looking at general stochastic PDEs that take on this form at the top of the slide. So we have some sort of a parabolic operator acting on our solution A, and on the right-hand side we have some generic nonlinearity, which depends on A as well as its jet, and this sort of exogenous term psi, so which often we think of as the noise in the PDE. And the components of A are going to be indexed by this index set, which we call L+. So L here stands for labels. And, okay, and so yes, so all the components I've described here. So the thing to keep in mind is that these A's are going to be taking values in some sort of a vector space W, and these noises, which are going to be indexed by L-, they're going to be taking values in WL. We can think of everything as being just defined in RD for now. Yes, so this F, as I said, is a smooth function that depends on the jets of the solution, the noise. So we're particularly interested in singular equations. And by singular, we mean that there are some products inside the equations that are ill-posed using classical methods. So one which I think many people are familiar with is something like the 5-4 equation. So here, psi is a 4-dimensional space-time white noise. So there's 3 spatial dimensions in one time dimension. And then basic Schauder estimates tell us that we can at best hope that the solution A is going to be a distribution. So then this cubic term in red is ill-defined. So we don't really know how to make sense of it in a classical way. So by the way, I'm quite bad at noticing if there's any questions in the chat. So please just interrupt if there are some questions and let me know. I might ignore it for a while otherwise. Okay, so I just want to now describe the existing results that are able to handle such equations. So there's indeed quite a well-developed now theory to solve such stochastic PDEs, provided that they're subcritical. So there's an essentially automatic procedure to compute a finite number of counterterms, which I'm going to denote with epsilon, and they're indexed by some sort of relatively natural objects, so this T-, but for now we can just think of T- as being some finite index set. And these taus, which are eventually going to be trees, we can just think of them as index elements. And these counterterms are going to be functions of the jet of A, and as well as these constants that only depend on the law the noise, and these constants are typically diverging, such that if we mollify the noise and solve the corresponding smooth PDE now, and we send the mollification parameter to 0, then solutions to this new equation where we inserted these counterterms are going to converge locally in time. This is the way to build solution theory for these types of PDEs. So then one of the issues that one runs into when trying to solve SPDEs where things take values in vector spaces is that the current results are formulated really for scalar equations. So that is, each one of these vector spaces W is just one-dimensional. So the topic of the talk will be how we attempt to get around this issue. Okay, so we can notice immediately actually that in principle this fact that these results are formulated when W are all one-dimensional is in principle not a problem, because these label sets L- and L+ are allowed to be arbitrarily large. So we're really able to deal with systems of scalar equations. So then, so a natural way to use the current setting is that you just choose a basis for each one of these vector spaces. You write the noise in the solution in coordinates, and then the existing theory tells us that some renormalization is always going to be possible. So there is some solution theory already. Okay, so what are the actual drawbacks of carrying out this solution theory through a basis? So first of all, it relies on this arbitrary choice of basis, and it's not obvious necessarily how to choose this basis in order to assist with computations. And in particular, this procedure breaks the natural vectorial structure that we see inside these stochastic PDEs. So that might essentially the counterterms might become difficult to compute in this way. So the example, as I mentioned, that I'll focus on at the end of the talk, and I'll give more details then, these stochastic Yang-Mills equations. So the way this equation looks like is the leading order is just an additive stochastic heat equation. So this size is based on white noise. But then the nonlinearity is naturally written in terms of Lie brackets, where this A takes values. So this is a one form taking values in a Lie algebra. And so if we were to write this whole thing down in coordinates, this would be a system of D times the dimension of G scalar equations. And then sort of working with a basis can hide a lot of the nice features that a Lie bracket encodes. So you would have to sort of work with the structure constants of the Lie algebra. In principle, that's also not a problem, but it's sort of you kind of you want to really just work with the Lie bracket rather than this choice of basis. And then, so okay, having said that, it's not difficult to convince yourself that this sort of different choices of bases really should correspond to the same notion of solution. The sort of this very fact that your choice of basis, when doing, if you were to carry out this sort of most naive sort of approach that I described at the beginning, the choice of basis shouldn't matter, already dictates that there should be a way of really solving the equation and doing all of these computations without ever introducing them. And this is what we kind of want to do. Okay, so I'll just spend 2 slides discussing the motivation behind the construction. So I've motivated the problem, and now I want to motivate a bit the construction. So I just want to recall some very basic elements of regularity structures. So so I'm going to ignore anything to do currently with analysis, and actually a lot about the algebraic aspects as well. So for me right now, a regularity structure will just involve 2 objects, which is a linear space T and a linear map that takes elements of T into the smooth functions on RD. So these are two of some of the elements that appear in regularity structures. So we should think of elements of T as being terms in the formal expansion of the solution. So if we recall that we're trying to solve a PDE like this, then we can just hit both sides with the Green's function of this heat operator. Okay, yeah, I've restricted now to the heat operator, but in principle, this can be any parabolic operator. And we see that A is given by a fixed point to this sort of convolution integral equation. And if we expand F in a Taylor series and we feed the solution back into itself, we're going to get a whole bunch of sort of formal terms to do with this exogenous term psi. And on the next slide, I'll give a non-trivial example of such a term. But for now, I'll just look at the most basic term, which is just psi itself. So somehow this element linear space T should encode this element psi itself. So let's just first suppose that psi takes values in a vector space W, which is n-dimensional. So if we were to apply the scalar setting that I described before, we would fix a basis E1 up until En of W, and then take corresponding elements, which I've denoted here, sort of circle 1 to circle n, which are going to be basis elements spanning some subspace of this linear space T. And then this pi is going to map each one of these circle I to psi I, where psi I is the expansion of corresponds to the expansion of psi in terms of this basis. So we can always write psi uniquely in terms of this basis, and then we do this corresponding matching. Okay, so this would be the scalar setting that we want to do. Then so a more natural approach would really be to not break apart this psi and really just work with one fixed symbol, which here I denote as a circle. And to this one fixed symbol, we just assign a corresponding subspace, which I've denoted T of this circle here, which is isomorphic to the dual of W. So isomorphic to W star, which is the dual of W. And then, so it's canonically isomorphic to this guy. And then for every element X inside this this T of circle, what pi of X will look like is that we just test psi against X. And this is again going to give us a swing function. There's obviously a natural correspondence between what's in blue and what's in red, in that these symbols, circle 1 until circle n, they're going to be the dual bases of E1 up until En. This is how we move between the blue and the red. But I think most people agree that at least this blue is perhaps a little bit more natural or maybe canonical, because at least it doesn't require us to ever speak about a basis. Okay, so that's the first part of the motivation of the construction. We're in a very simple case, so let me look at a slightly more complicated example. So suppose that inside of our PDE, we had another noise psi bar, which now took values in W bar. And we really want to treat this separately from psi. For maybe psi bar has different regularity, or it just appears in a different way in the equation, but we don't want to combine the two. So then, as I said before, elements of T look like terms in this formal expansion of A, and it turns out that these terms can all be indexed by trees. They all quite naturally look like trees. So it's helpful here to have a graphical notation. So I'm going to, in terms of psi, I'm going to denote this before by the circle. In terms involving psi bar, I'm going to denote by this dark circle. And then lines inside of these trees, they correspond to convolution of the Green's function. So for example, a term like this would look like some sort of a function. So if you just stare at this correspondence long enough, it's sort of becomes clear how to move between trees and functions and back. So in particular, whenever we join three lines at a root, so whenever we join lines at a node, that means that there's a multiplication of functions. And whenever we move down towards the root with a line, that means we can roll with the Green's function. Okay, so then how would the scalar setting look like here? Well, to every light circle, we would assign an element EI of the vector space W, and to every dark circle, we would assign a basis element E bar of W bar. And then for each possible labeling like this, we would have this map pi map us to a smooth function. So given what I said on the previous slide, it becomes a little bit more natural to associate with this tau, again, a subspace of this regularity structure T, which we want to sort of be isomorphic to this tensor product of the duals of W and W bar. So we have W star appearing twice here because we have two noises with shaded lightly, and then W bar appears 3 times because we have 3 of these nodes. But the catch here is that the tree that I've chosen to draw here, its left 2 branches are symmetric, so they look identically. They look identical, and because we're essentially looking at so multiplication of real valued functions is commutative. So any sort of operation that we define on this tau should be invariant under permuting these 2 branches. So essentially we're looking at combinatorial trees rather than planar trees. So so we really want not this whole entire vector space, but we really want a partially symmetrized subspace, which is invariant under permuting the sort of the first 2 and the 3rd and 4th entries, invariant under this permutation map. Okay, so as I said before, in the talk I'll describe how we handle this in such a way that this sort of symmetrization happens automatically, and such that all the sort of nice properties that we know from regularity structures, such as having a coproduct structure in certain spaces and having that coproduct multiplicative and co-associative, sort of works automatically. Okay, so
may I ask a question?
Yes, of course.
Before you talked about the noises and you associated dots, and then you said you go to this subspace defined through the noise or the noises.
Mm-hmm.
Now you have a tree. The tree is made out of these vertices. So for each tree, you would look for a different subspace, or how is this? What makes this tree now so particular? Or for every tree, you will have to do specific subspace. Or I don't understand.
Yes, that's the idea. So for every tree, there was going to be a subspace inside the regularity structure. So in this here, I was trying to motivate how the subspace associated with this tree should look like.
Okay.
But for a different tree, you will have a different subspace.
Okay, thanks.
And that element will be something I will try and discuss in a few slides.
Yeah, maybe another question.
Yes.
So in the expression at the bottom,
mm-hmm.
You would always want to keep the x5 on the right. I mean, you would never exchange it with any other or the red or the blue terms.
So so the fact that I've chosen to just label x5 on the very right is was in some sense a choice here. Like I could have put this W star at the very beginning and like reordered these vertices to be kind of like going in the other direction. So it's not so important that it's sort of at the end, but what's important is that if I was to move it, like I would have to move it independently of the other vertices. But so basically, whenever I move the x1 and the x2, they have to move together.
Yes.
So this particular ordering is sort of like a choice of representative of the kind of like the vector space that I'm interested in. And once I've chosen to put x5 at the end, then it sort of has to stay there. But these two pairs can move around.
Okay, I see.
Yeah, if that makes sense.
Yes, thank you.
Okay. Okay, so let me try and give just a very general idea of how this automatic symmetrization procedure is achieved. So what we do is we're going to define a category, sort of invent a new category, which we call symmetric sets. And the main example of these of the objects in this category are going to be trees and forests. Then we're going to define a functor that moves from S set to vector spaces, and this is this automatic sort of symmetrization procedure. Then the idea is that the usual operations on trees and forests, such as multiplication of trees, where we just join their roots, or extraction contraction of certain forests, are going to be realized as morphisms inside this category. Then the way that we define the regularity structure is going to be given by this direct sum of subspaces, which are indexed now by these trees. So this is in some sense related to Karush's question, where these subspaces that I was talking about before, associated to the noise and associated to that tree that I looked at, are going to be components of this big regularity structure given by all the possible vector spaces. Direct sum of all these possible vector spaces. And then the key point, what motivated this construction is that the functoriality of this functor f allows us to move nice combinatorial identities from the level of the trees directly to these symmetrized vector spaces. Some particular we can define coproducts directly on this vector space by understanding how they work on the level of the trees. And then moreover, this formalism allows for relatively straightforward computation of these counterterms, which can be quite nice. Okay, so let me first coming to a couple of now details in the talk. So I want to give an indication of what this category of symmetric sets looks like, as well as morphisms between them. So we're going to consider a finite set L, similar to before. So we should think of L here as indexing all the components of the solution as well as the noise. And so elements of this L are going to be called types. And a type set is a pair of a finite set and a map that to every element in this finite set associates the type. So then a symmetric set, an object inside this category, consists of the following objects, the following features. So it involves an index set A. So then for every element inside this index set, we're given a type set TA and this, so TA. And then for every pair of index sets, we're given a non-empty set of type preserving bijections, taking us between TB and TA. So this ISO denotes type preserving bijections, which has the following groupoid structure. So if gamma belongs to one of these sets, gamma AB, and gamma inverse should belong to the other corresponding set, and also it's closed under compositions. Okay. So just a remark is that the fact that these gammas are non-empty means that all of these sets TTs that appear inside this definition of a symmetric set, they're all isomorphic. So there's at least one type preserving bijection between them, but non-canonically so. So there's these gammas, they don't have some sort of a fixed like a distinguished element that tells you precisely how these type sets are isomorphic to each other. In some sense, just like when you draw two trees and they're isomorphic, there might not be a canonical isomorphism taking one to the other. Okay, so I'll give an example of the most important type set that of symmetric set that we look at. In fact, the only one relevant for this work. So a labeled rooted tree, a bit similar to what we saw before, consists of a tree. So V denotes the vertices, E denotes the edges, which has a distinguished root, which we denote by rho. So this map T is going to be a map from all the edges into some label set L. So we only type the edges, and also possibly some other decorations. And the one that at least those who are familiar with some works of regularity structures will know that there's this map N that sort of denotes the polynomial terms or derivative terms that you put on the vertices or edges respectively. Okay, so the fundamental aspect is these first 2 points, and then the third one kind of denotes these extra labels that we put onto the tree. So then tree isomorphisms are bijections. So it's a bijection between the two trees, taking the edges of one to the edges of the other, which preserves all the relevant structure. So it preserves the root, it preserves the connectivity, it preserves all the types, and preserves these extra decorations which you choose to put onto the tree. So then the symmetric set associated to a labeled rooted tree, the index set A, which is going to be an infinite index set, it's going to be the set of all trees isomorphic to tau with some concrete set where you allow the vertices to vary over. So for example, for concreteness, you just pick some countable infinite set like the natural numbers, and you allow the vertices of these trees to be these elements of the natural numbers. So that's the index set. Then these typed sets, they're going to be all the pairs of the set of edges with the corresponding type. So recall that a label tree has this has a type going from the edges to the set L. And then these gammas, they're going to be all the tree isomorphisms that take edges of one tree to edges of another tree. So notice that this gamma is typically going to be a strict subset of all the type preserving bijections of between the two relevant edge sets, because there might be a type preserving bijection between the edge sets, but it doesn't preserve some extra structure that you imposed on the tree. So it might not preserve the root, for example, in which case you don't allow this type preserving bijection between the two edge sets. So this is why so here this on the previous slide, this is why we work with a strict subset of the type preserving bijections rather than all of them. Okay. Okay, so I've talked about the objects that appear inside these this category of symmetric sets. So then, what about morphisms? So I'm going to spend a little bit less time in explaining how the morphisms look like, because it's a slightly technical point of how to get it to work correctly. But I'll present the construction here, and I'll answer any questions if there are any. So let's consider first just the fixed type set T and some arbitrary symmetric set S bar. So we first define this the set Helm bar between T and S bar, which consists of so recall that S bar contains a lot of copies of different type sets, like T bar or something like this. So we look at all the maps, type preserving bijections from T to these elements of S bar. So this is this whole big set. And then we quotient by the action of this gamma that appears in the definition of S bar. So what that means is that for two different type preserving bijections, phi and phi tilde, whose targets could potentially be different sets. So for example, phi could have a target TA and phi tilde could have a target TB. So for any two of these guys, we say that they're equivalent if there exists one of these gammas inside gamma S, which goes from B to A, such that this sort of natural composition between phi tilde and gamma is equal to phi. So in some sense, when looking at this phi as a map to S bar, you can't distinguish between phi and phi tilde whenever you allowed to reorder things by this set gamma. Okay, so it's the first step in this construction. So then, given another symmetric set, we define a natural object, which is essentially just the space of sections. So this is a vector space where sort of each fiber is essentially the element. So it's so if I look at an index set, an index element in this index set AS, then it gives me a formal linear combination of these elements hom, where I replace T by TA. So it's sort of like if you think of S as being made of a whole bunch of fibers, I just independently of each other, for each fiber, I give you an element of this hom bar. Where again, I recall that I have this quotienting on the target space. And then a morphism now, so finally I get to the definition of what an actual morphism is between these type sets, is that I now link up all of these definitions, link up all of these choices of phi A between the different fibers by essentially making them invariant under the action of gamma now in the domain, so for S. So it's essentially all of these choices of sections, such that if I move from some fiber B to A, and I look at this element phi A here, it's going to have to be what I started with above phi B, and this is for all pairs of indices in the symmetric set A and allowable type preserving bijections gamma. Okay, so this is when you first see it, it's perhaps a slightly complicated thing to try and digest, but it turns out that this sort of quotienting on the target space and having this invariance under gamma on the domain is quite a natural way to view it. Okay, so how does this relate to this? Okay, so what I just said finishes the description of the of this category symmetric sets. So now I want to describe this functor that I mentioned that takes symmetric sets to vector spaces. So consider some vector space assignment V, which is indexed by so for every element of this label set L, I give you a different vector space. So then for any type set, I'm going to denote V capital V tensor T to be this tensor product between where I vary over all elements of T, and I take the corresponding vector space V, which is given by the value of this map T at X. So then for another type set and some type preserving bijection between T and T bar, it's quite clear that there's this type preserving bijection induces a vector space isomorphism between these corresponding vector spaces, which is so for every element Y inside T bar, it's just given by looking at the pre-image of Y under gamma. So this is how it looks like for elementary tensors, and then the definition is extended linearly to the full tensor space. So for symmetrics, so now looking at an actual symmetric set S rather than just typed sets, we define this V tensor S as being a very small subspace of this big sort of infinite product, or potentially infinite product, where so we take the direct product of all of these V tensor TA, where TA varies over the type sets inside of the symmetric set, subject to the sort of a natural invariance condition under the action of gamma that we saw for morphisms. So if I look at the value of if I look at the vector V sitting above the type set TB, and I hit it with this gamma that transfers from B to A, and now this gamma here I interpret as a natural sort of vector space isomorphism up here. It has to be whatever's sitting above VA. This is a very similar thing that we saw for the morphisms. And yeah, right. So as I said before, this V tensor S space is going to be typically quite small, so much smaller than whatever this is. So in particular, its dimension is going to be bounded above by the dimension of V tensor TA for any of these elements A. In fact, all of these dimensions are going to be the same as we vary A. So in particular, if all of these vector space assignments that we started with are finite dimensional, then this dimension is also, the dimension of this V tensor S is also going to be finite, even if the indexing set is infinite. Okay. So this is how we assign to every symmetric set a canonical vector space. So this map that we call F, and now I've added a subscript V because it depends on this on the choice of vector spaces V that I started with, that takes S to V tensor S, takes objects of the symmetric set to objects of in vector spaces. So then an important and the fundamental thing here is that this map actually extends to a full functor between S set and vec. So it maps morphisms between S and S bar to linear maps between these the relevant vector spaces. So it takes any morphism phi to this function f of phi. And I'm not going to give the full construction here, but I'll just, in fact, maybe once you see this definition, it becomes sort of clear how to extend it to a full functor. So the way that it looks like is you take an element. So to describe how f of phi looks like at an element V inside this tensor product, you first inject, so there's a natural injection that moves from V tensor S into any one of these representative subspaces. So in particular, this line sort of tells you that V tensor S can really be seen as canonically as a subspace of this V tensor TA, where TA is some element of your symmetric set. So you first apply an injection, then you look at phi A, which is again just a representative of this HOM lifted to the vector spaces, and this takes you between V tensor TA to V tensor T bar A, and then you apply symmetrization map that takes you back into V tensor S bar. So there's sort of two fundamental maps that so an injection and a symmetrization that are used in the definition of this functor. Okay, so I'll just try and be content just with giving the statement of the lemma and not a full proof. Okay, so back to so moving out of this abstract category theoretical definition, I want to now move back to the concrete situation for regularity structures. So how's this abstract definition useful? So for any choice of at least finite dimensional vector spaces V and a rule R, which is this rule will probably be familiar to people who are familiar with regularity structures, but just this rule R kind of comes from the equation that you're looking at. This construction quite naturally defines a regularity structure. So as I said before, you define it to be this the direct product of all sort of admissible trees that it might appear inside the formal expansion of your solution, and you apply this functor that I just described to them, where you now view tau as a symmetric set in the same way that I described a few slides ago. So this gives you this sort of like relatively straightforward definition of a regularity structure. So then replacing trees by forests, you can certainly define sort of a linear space of forests. And the key point, which I said in the sort of the general idea section, is that combinatorial identities for trees and forests pass through this functor directly to these vector spaces. Okay, so I want to give an example of how this might look like. Recall that if we have a subforest of tau, which I denote by this sort of injection, so F is some sort of a forest. So here we should think of F as this red forest consisting of two trees, which I've denoted in red here, and we inject it into a tree tau. So we identify some roots, so some edges and vertices of tau with those of F. Then whenever we do this, there's a natural contraction extraction operation that can happen. So we extract this forest to get it back here on the left, and where the forest was sitting inside the tree, we contract it to 2 points. Well, we contract it to a point. So if we contract this this tau by this forest, we end up with this tree over here, which is here it's denoted by tau slash F. Okay, so such an embedding of a subforest into tau gives us this sort of object on the right. So every choice of a subforest injected into tau gives us a morphism inside the symmetric set, this category of symmetric sets. And this morphism goes between tau into this object that we had on the right. Oh, and now this tensor product is treated as the the free product of two sets. So they're disjoint, and so it makes sense to consider tensor products of these symmetric sets. And so the way this morphism is identified is, or the way it's constructed is that this injection of F into tau tells you how to identify the vertices on the right with the vertices on the left. Okay, so it's not saying anything much more than that, really. Okay, and so the nice part about this is then this the fact that we can encode a contraction extraction operation as a morphism inside the symmetric set allows us then to sort of automatically push this to a linear map between this T, which is our regularity structure, and sort of a tensor product of forests with trees. Okay, and this is just given by looking at all the possible embeddings of forests into all trees that we care about. So okay, this notation is not quite strictly speaking correct. I should really define what this thing looks like on the tree with on each component of T. But I hope the sort of notation is quite clear. And this is modulo combinatorial constants and also sort of completions of tensor products, because these are all sort of infinite series. So it's not quite right to just look at the simple tensor product here. Okay, so this is just to give an idea of how this functor acts. Yes, so then as I said, the fact that this f is a functor implies that we can really work with this delta map. So x here stands for extraction. So it tells us that it sort of inherits many nice properties that we're familiar with for trees and forests. So in particular, it allows, without thinking, to prove things like co-associativity for variants of this type of map.
Ilya, may I ask a question?
Yes, of course.
I think I probably missed this point, but your trees are, to begin with, non-planar, right?
That's right. They're combinatorial. Yes. Yes, which is part of the whole thing, that they might have these symmetries.
Okay.
Yeah, exactly.
I would like to, because okay, you encode the symmetries. I mean, in your spaces.
Mm-hmm.
You may have the extreme case where you have no symmetry at all. I mean, if you put like for every noise a different space.
Mm-hmm.
So
okay.
Here you work in a planar case, or it's not?
Here we work. Sorry.
When you have you associate to each noise, I mean, a different vector space.
Mm-hmm.
So you have any symmetry on the tensor product. So are you there in the planar case?
So there there effectively you're in the planar case. So there this functor f applied to this tree that has no symmetry is just going to be canonically isomorphic to the classical tensor product between the associated vector spaces.
So the coproduct that you would, I mean, this extension to the coproduct would be a coproduct on planar trees?
No, it's still going to be a coproduct for planar trees. So this coproduct actually, so we no longer think of these trees as indexed like as basis elements of the relevant algebras or regularity structure.
Yeah.
They're really index subspaces now. But these subspaces, so the trees that index these subspaces, they're still going to be non-planar. So if you have no symmetries in your tree, if you permute all the branches, that's well, I guess it's still the same tree. So maybe I was wrong to say that you're effectively in the planar case. So no, we're still always in the non-planar case. I'm not sure if that answers your.
I mean, you can move on and then.
Yeah. Okay. Yeah. So maybe it will become perhaps a bit clearer. So, but yes, I think we're always in the non-planar case, if I understand your question correctly.
Okay.
Okay. So just to summarize so far what I've said. So we've defined this vector space T, given us the push forward of all of these trees to vector spaces to the functor. So tweaking this construction of the delta extraction that I just described, and essentially using the results that are currently known for regularity structures, you get two Hopf algebras F minus and T plus with associated coactions, comodules, and you get character groups, which are finite dimensional renormalization groups. So these are all sort of like the familiar sort of elements that appear in regularity structures, and you can essentially take all of that machinery and push it forward to the setting of vector spaces through this functor. And the whole point was that we never really needed to work with the basis for this. So then a couple of remarks is that this construction is compatible with decompositions. So if we were to decompose the labeling set somehow. So if we were to take each one of these elements of each one of these types and map it to some another set of types, and we have a corresponding decomposition of vector spaces, then there's a natural, I think in category theory, I guess it's called a natural transformation that takes shows you that these sort of like decomposing first and then taking the functor is the same as just taking the functor itself. So then, okay, minor point, this thing resolves some ambiguities when you're working with trees versus isomorphism classes of trees. Although this hardly really ever bothers anyone, but it sort of actually bothered us a little bit when we started to think about this, how to do this properly in the vector space setting. And also for simplicity here, and also actually in the paper, we ignored this business with extended decorations. It was sort of like in the background. But the construction should definitely work if you were to do it honestly with extended decorations. Okay, so I haven't actually said so far how we choose these space assignments V. So I remember at the beginning I talked that the components of the solution and the noise take values inside some vector spaces W, and then I used V to as the space assignment when talking about this functor, and chose a different symbol for a reason, which is that the W's are not the same as really as the V's. So going back to the SPDE, how do we actually decide on how to choose these V's? So yeah, recall the noise take values in this WL, the solution take values in WT, and it was trying to solve an equation that looks like this. So then it turns out quite natural to take, and I've really, I think, partly motivated this at the beginning when I talked about with the examples of the trees, maybe the third and fourth slide. These V's are going to look like essentially duals of W. So in a tree, if I see an edge which is labeled by a noise, I take W star, so the dual space where the noise takes values, and if I see an edge which labels an integration kernel, I just label it with R. So the corresponding vector space is going to be R. So then there's a bit of asymmetry here, and just to sort of describe why this asymmetry happens. So it's natural to take this choice whenever T is corresponds to an integration kernel, because this G is not a variable in the solution that so G is fixed. It's not something that we ever have to solve for. So it's not something that can vary. But it is natural in some other settings. If you were to apply the setting that I just described to some other equations, it could be natural to take V, which is not isomorphic to R. So for example, in quasi-linear SPDEs, this function G is no longer fixed. It actually depends on the solution A. And so for every occurrence of the integration kernel, you would want to associate a vector space which parameterizes all of these heat kernels, where you have a different factor in front of the Laplacian. So you let the C vary from 0 to infinity. So this trick of associating to every integration kernel some infinite dimensional space, which is able to parameterize all of these kernels, this is a trick that was already used by Mate and Martin in an earlier paper. So this sort of systematizes and generalizes this trick. Okay, so this is the way that we pick our vector space assignment in our case. So then, okay, I'll just spend a couple of minutes looking at how one would lift canonical models, because I think that this kind of it's quite simple, but it tells you how these spaces look like. So then, as before, if we fix two noises now, xi and this is supposed to be xi bar, taking values in W and W bar. And now, as I said before, we look at them as we think of them as being edges to match the previous construction. But they're terminal edges, so that they're represented by nodes, but you should really think of this as like a dangling edge. So then if we look at this tree that we had before, the functor applied to this tree is going to be canonically isomorphic with a subspace of this tensor product, which is invariant under permuting the red and blue factors. So, and then the canonical model associated with this xi and xi bar is, okay, now I've gone back to xi1 and xi2. So for every element x1 to x5 inside of this tensor product, or the subspace of this tensor product, I'm going to associate a function of z, which is given by products of these iterated convolutions with the Green's function. And sort of the point here is that, so I guess the point of this slide was to sort of motivate why it's natural to put W star here, for example, because this W star gets inner producted with the noise. So this x1 has to live in the dual space of wherever this noise lives. So you can sort of see that swapping x1 and x2 with x3 and x4 doesn't change the value of this function, which is why it's natural to work with this partially symmetrized subspace. Okay, so this is how, so just an example of how canonical models look like. Okay, and so then, so what about the actual counterterms inside the SPDE? So I know I'm almost out of time, but I'll try and quickly go through this. So recall we wish to obtain solutions to PDEs that look like this. So then before we added a finite number of functions of A to this SPDE. So how is it natural in this framework to encode these counterterms? So it turns out that this original family of functions f that appeared on the right-hand side of the PDE defines a family of maps upsilon on the jet of A and psi. So here we treat A and psi on a slightly more equal footing than previous works. And the catch is that it doesn't only take values in the space of wherever A lives, so this W, but you keep track of the tree that is associated to this upsilon. So in the scalar setting of this, all of these things would this functor would just map it to one-dimensional subspace. So this would really just give you something in W. But if this tree has if the vector space assignment was not scalar, then it's natural to carry along this this vector space in the definition of upsilon. Then these the sort of BPHZ constants that appear in renormalizations are naturally going to be elements of the dual space of this this functor applied to this tree tau. And then you can write down these the renormalized equation in quite a concise way. So you have your original right-hand side, and then you add to it something that looks like this. So you have these epsilons, which are now functions of A and potentially other stuff. And now you recall that upsilon takes values in this tensor product, and then this BPHZ constant is a dual element of whatever appears of the left factor. So you can contract this the two left factors to give you a real number. And so this whole thing on the right-hand side now takes values in WT, which is where A takes values. This sort of makes sense. Okay, so this is a way of writing down these counterterms again without necessarily introducing a basis. Okay, so I think I don't necessarily have much time left to discuss how to apply this to our specific equation. Okay, I can just present maybe perhaps the result, which motivated this whole construction. So the stochastic Yang-Mills equations, I drew them before, but now here they are in a little bit more detail. So they're given by a natural gradient flow of some energy. And we add a noise to the system to get, so it's a natural Langevin dynamic. And so yes, in coordinates, it's a little bit complicated to write down. And so then this right-hand side, the noise with all of these Lie brackets becomes our choice for F's. Now they only depend on A and the gradient of A as well as the noise. And all of these things take values. And so A are one forms that take values in some Lie algebra. This Lie algebra is the Lie algebra of some compact Lie group. And these psi's are all IID G-valued white noises on actually, sorry, there should be RD plus 1, so they have one extra time component. Okay, so then so sort of the main sort of theorem of the work for which the part of which I just described here is that if we're working in 2 dimensions and with periodic boundary conditions, then for any constant c, we have convergence as epsilon goes to 0 of the Yang-Mills equations, where we simply add this CA to the right-hand side. So there's a slightly strange renormalization in the sense that you don't really need renormalization. You can just, so the equation actually makes sense without any anything on the right. You have this choice to add it if you want. And this choice becomes important for the second part of the theorem, which is that under certain conditions, like the fact that G is simple, and that the mollifier that we've chosen to mollify the noise with is non-anticipative. And if we choose C in just the right way, so given by sort of something to do with the Green's function, hit with the mollifier and all multiplied with lambda, where lambda is the value of the Casimir in the adjoint representation, then this whole limit goes as epsilon goes to 0, converges to a nice Markov process that has a gauge invariant property. Okay, I'll just ignore that point. Okay, so I think I don't have time to actually describe, unfortunately, the rest of the construction, but maybe I'll just go to the final slide. So there's essentially 3 trees. So I can outline the proof of part A. There's going to be 3 trees that that ultimately contributes to the renormalization, and the other trees you can cut out using basic symmetry arguments. And so colors here are going to denote the spatial components 1 to D, so 1 and 2 in our specific case. Then so this one of the VBHZ constants of, say, for this tree will look like some C epsilon, which diverges like log of epsilon, multiplied by the Casimir. So recall that this L belongs to should belong to the second tensor space of wherever the noise lives. So essentially this Casimir element is like the expected value of the noise. Okay, so and then these upsilons now take values in this second G star tensor G star tensored with G itself, and so, for example, for the single tree, which is the cherry, it's going to look like an element of the space on the right, where so the basic object that we start with, this psi, is going, we identified with the identity element inside G star tensor G. And so you can use the right part, which is G, you can use inside the natural sort of function f that we started with for the SPDE. So this function f contains these Lie brackets. So you can use this right factor of this psi associated with the noise to bracket it with A. So this, and then ultimately you get something inside of this space here. And so again, this BPHZ constant, which lives inside G tensor SG, is the dual of this space. So it makes sense to contract the two. So then contracting the two gives you a sort of a mass renormalization term here. And so then the rest of the proof is just that you do a similar sort of computation for the other two trees, and you sort of see that they cancel the divergent part of this thing that we looked at. So the point here was really just to illustrate where these L's and these epsilons live for a specific example, and that they're actually not. So the setting might have been quite abstract to begin with, but when doing these concrete computations, they're actually quite helpful. Okay, so that's all that I wanted to say. So thank you very much for your attention.
Yes, thank you very much, Ilya, for the talk.
Thank you.
Are there any question?
Yeah.
Yes.
So is it right that you could do everything without this machine, right? Sorry, my son is woke up. Right? So
No
you could do everything without this machine, but this machine provides you with a more natural or somewhat more efficient way of dealing with this problem of vector valued SPDs. Is this,
that's correct. Broadly speaking, that's exactly what it does. Yeah. So as I said at the beginning, you can just write everything in coordinates, and it's not even that difficult to see that the ultimate answer that you get should be independent of these coordinates. But then this very fact sort of suggests that it should be possible to do everything without at the beginning introducing these coordinates. Yes. So.
Thanks. Sorry.
Yeah, so maybe I have another question. So this construction you have of taking vector spaces and tensoring them together according to trees is something that you will also see in some description for operands. So is there any relation?
That's a good question.
Also including the symmetries, even if you talk about symmetric operands, that you can permute subtrees that are symmetric.
So I'm definitely not an expert in operands. So I wouldn't be surprised if certain elements of this construction definitely appeared elsewhere. And it would be actually quite nice to. I mean, I would be. Well, it's not. I'd be surprised if precisely this sort of construction appeared, but I certainly wouldn't be surprised if certain elements of it appeared in other places, and perhaps actually in
just a remark. I mean, this tensor product of vector space. I mean, we already use this for in the paper stochastic geometric stochastic integration.
Right. Yeah.
Using some kind of properad structure to describe the U epsilon and the morphism properties.
That's right. Yeah.
So I'm not sure, but your construction, your algebraic construction, is very close to the species formalism of André Joyal, which is used in operad stuff.
It's similar to the species construction of what? Sorry.
The species formalism.
In operad.
Yeah.
Yeah. So this is something that yes, it would be good to actually make to make precise. So I'm not. Yeah, I'm definitely not. I don't want to claim that everything in this construction is somehow completely original.
Yeah.
And it would be good to figure out whether there's actually a way to streamline it.
But usually for trees, it is used with respect to vertices, and here you use it for edges. So I don't know what comes out, but it is the same. I guess it is quite the same formalism.
Yeah, I would have to look into it. But yes, thank you for the actually.
Do you have a reference, Dominique, about it?
Yes, there's this lecture note by André Joyal, and it's easy to remind because it's 1, 2, 3, 4. Lecture notes Springer 1, 2, 3, 4. On,
okay.
But I'm afraid the paper is in French. Sorry.
No, this I might be able to actually read.
But you are fluent in French, no, Ilya?
No, I'm not fluent, but I maybe some mathematical terms I can understand.
I use it with Loïc and Frédéric Fauvet in our finite topologies paper.
Well, maybe if the fact that it's in French, it explains why a Google search didn't reveal any obvious similarities with known literature. It's obviously searching in English, so that was.
Also, Yannick mentioned in the chat that you have some introduction by François.
Ah, yeah. Okay, good.
Thank you. That's good to know.
There's a book by Bergeron and some other people on species, right?
Bergeron, Labelle, Leroux, yes.
Yes.
Yeah, okay, if there are no more questions, then I'll just stop the recording and then we can discuss freely. Okay.